Hello, Mr. Betts here. I would like to add to the toolbox of shortcuts that we have for taking derivatives. So, in the last section, we talked about the power rule and how we can use the power rule to take derivatives of a very specific kind of function without having to use that limit definition of the derivative. And we're going to expand on the power rule with four new rules that will allow us to take derivatives of more of a variety of types of functions. So, here are all four of the new rules. So we have a constant rule that says that if we have a function, say like y equals k, or y equals, I'm going to use a specific example here, say y equals 7, then the derivative of that is just going to be 0. So the derivative of any constant is going to be 0. And I'll talk in a minute about why that's the case. The sum and the difference rules are really the same thing. And they both basically say that if we have a function that has multiple terms, so in this case I have two terms, but this could be expanded to include 3, 4, infinitely many terms if you want. If we have a function that has multiple terms, then what we can do is we can take the derivative of the individual terms and then add them together. Or with the difference rule, if we're subtracting terms, then we subtract them. They're really the same thing because if g is some function that's negative, it's the same thing as subtracting the opposite of g. So sum and difference rule, basically the same thing. Constant multiple rule. Sorry, we don't want to get confused with the constant rule because that is different. The constant multiple rule says that if we have a constant that's multiplied by some function and we want to take the derivative of that whole thing, we can take the derivative of the function and then multiply that derivative by the constant. So this is going to be really handy with mixing it with the power rule. So let's say we have a function that is like y equals 3x to the 7th power. Well, what that allows us to do is take this 3 here and multiply it by the derivative of x to the 7th. We can do the derivative of x to the 7th with the power rule. So dy dx here is going to be 3 times, and then the derivative of x to the 7th is going to be, with the power rule, 7x to the 6th. So that's going to be 21x to the 6th. So this rule here allows us to take derivatives using the power rule, but also terms that we would see in a polynomial that might have a coefficient besides 1. So actually combining the power rule with these four rules, we can take the derivative of any polynomial. And that's something that we're going to do in another video. So I want to take a little bit of time here and talk about why each of these rules work. I think it is important for us to understand this, but using these rules, we're going to be applying it to taking derivatives. I'm not necessarily going to expect you to recreate any of these explanations. So first one here, constant rule. Let's say we have a function that's like y equals 7. That's the example I gave earlier. Y equals any constant. If we were to graph that, it's going to be a horizontal line. If we are taking the derivative of a function, remember the derivative means the slope of the function at any given point. Well, if I pick any point on a horizontal line, the slope is going to be 0. So this horizontal line has a slope of 0 at all points, so the derivative of this function is going to be 0. Okay, so the derivative of any constant is going to be 0 because we're taking the derivative of a horizontal line which has a slope of 0. The sum and difference rule, I'm gonna do these together, and I'm just going to do the sum rule, but you can figure out what that would look like for the difference rule also. I'm going to define the function a of x as f of x plus g of x. Okay, so a is some function that has two different terms, or really two different functions that are added together. And so the limit definition says that the derivative of a is going to be given by the limit as h approaches 0 of a of x plus h minus a of x all over h. It's going to take a little bit of algebraic manipulation here, but remember a is f plus g, so we can rewrite this as the limit as h approaches 0 of f of x plus h plus g of x plus h minus, I'm going to put this in parentheses here, f of x plus g of x. And that's still all over h. So then rearranging some things, we have f of x plus h minus f of x plus g of x plus h minus g of x. So I distributed that negative there, all over h. And the sum rule for limits says that we can take this and write it as two separate limits. I'm actually going to change this just a little bit here. And I'm going to write this as two separate fractions over h. And I think you might be able to see where we're going here. So this is going to be now limit as h approaches 0 of f of x plus h minus f of x all over h, plus the limit as h approaches 0 of g of x plus h minus g of x all over h. And this right here is the derivative of f. This right here is the derivative of g. So we get f prime of x plus g prime of x. And f prime of x is just another way of writing that. G prime of x is just another way of writing that. So again, this is not a process I would expect you to do on your own, but you can see using that limit definition of the derivative and using rules for limits, if we have the sum of two separate terms, we can take the derivative of each of those terms individually to get the derivative of the whole thing. Last rule, the constant multiple rule, I'm going to do the same thing. So I'm going to say, I'll use b of x here since I already used a of x. So b of x is going to be k times f of x, and I want to take the derivative of b. So it's going to be the limit as h approaches 0 of b of x plus h minus b of x all over h. So I'm going to replace the b of x's with k times f of x. So it's k times f of x plus h minus k times f of x all over h. We can factor that k out. So I'm going to save a step here. I'm going to do that in this step. And then there's a constant multiple rule for limits, if you remember when we were talking about limits, that says that we can basically take this k outside the limit. So this is equal to k times the limit as h approaches 0 of f of x plus h minus f of x all over h. And you might notice that this right here is the derivative of f. So this is k times f prime of x. So again, when we take the derivative of k times f of x, we get k times the derivative of f of x. And so again, this is a process that using the limit definition and just some algebraic manipulation, we can show that this constant multiple rule works, and then we would put it into use. So I already gave the example if a function is, I don't remember what I said, 3x to the 7th maybe. The constant multiple rule says that when we take the derivative of f, that 3 stays. We take the derivative of the x to the 7th. That's going to be like my f of x here. And that's going to be 7x to the 6th. That we're doing using the power rule. So that's going to give us 21x to the 6th. All right, so this constant multiple rule allows us to take the derivative of any term in a polynomial using the process that I just used here. And then the sum and difference rule is going to allow us to take the derivative of separate terms in a polynomial to take the derivative of an entire polynomial.